Welcome, everybody. Hi, my name is Dan Weimont. I'm a professor in atmospheric and oceanic sciences here at UW-Madison. I'd like to welcome you all to our annual Leonard Robock lecture. This lecture is made possible by a generous gift from the Leonard Robock estate. And the goal of the lecture is to bring in leading scientists to UW-Madison to speak on issues of broad public interest related to atmospheric and oceanic sciences. Before we begin, I want to thank a few people who have made this event possible. Rudra Thakur, who's helped with logistics. Liz Maroon, who's been running our entire colloquium series. And out in the hallway, Scott Dyke, who, we'll just give him a round of applause, who you met on the way in, who has been instrumental in getting this up and running. So thanks to all of you and to everyone else behind the scenes who helps make these events happen. It is my great pleasure to introduce this year's Leonard Robock lecturer, Dr. Clara Deser. Dr. Deser is a senior scientist at the National Center for Atmospheric Research and a former head of the climate analysis section at NCAR. Over the course of her distinguished career, her pioneering research has advanced our understanding of climate variability and climate change, with a particular emphasis on the interactions among the atmosphere, ocean, land, and sea ice. More recently, she's led the development and application of large ensembles, which we'll hear a little bit about today, I think. And those have fundamentally transformed how we interpret and analyze climate variability and climate change. I expect we'll hear more about some of that this evening. Across all of her work, Clara is known for her exceptional clarity of expression and her strong grounding in observations, qualities that are widely recognized and deeply valued within our community. It's no exaggeration to say that Clara Deser is among the most respected climate scientists in the world, I think. She has authored more than 200 publications and has received numerous honors, including the Roger Revelle Medal and election as a Fellow of the American Geophysical Union, as well as the Jewel Charney Medal and Fellowship in the American Meteorological Society. And in 2021, she was elected to the United States National Academy of Sciences. I was talking with Clara yesterday, and our conversation turned to the importance of mentoring students and postdoctoral researchers. And in this conversation, she looked at me and said, "That's what it's all about, isn't it?" I think that captures an important perspective on Clara's impact in our field as well. Throughout her career, she's mentored countless students and postdocs, both directly and through broader training efforts such as summer institutes and community programs at NCAR. Through her mentorship and through the example she sets in her research and leadership, she has helped shape a generation of climate scientists. I know many of us here today, myself certainly included, are grateful to count Clara as a mentor, a role model, and a friend. So please join me in warmly welcoming this year's Leonard Robock lecturer, Dr. Clara Deser.
Thank you everyone for coming, especially the week before spring break. I appreciate it. Thank you, Dan, very much for that introduction. And I'm really honored to give this Leonard Robock lecture today. I've prepared not too many slides. I don't want to make this, too long of a seminar, but I would very much appreciate any of your questions. I won't cover all aspects of climate variability and change. So if there's something you're interested in, I'd be happy to try to answer your questions. And feel free to ask during the lecture or at the end. Okay, so thank you so much, and thank you very much to the department. I've had a wonderful two-day visit and met so many people who have definitely reaffirmed my faith in our discipline and keeping our science advancing despite difficult times. Okay, so this is eye candy that you have on your brochure, I guess, and we will talk about what these maps are, but we won't do that until maybe halfway through the lecture. But I won't tell you what these are until we get to that time. So we've all very much aware of climate hazards, environmental hazards that are now worldwide. These are some iconic examples of, hurricanes, sea level rise, intense snowstorms, wildfire, drought, the melting of polar ice. And each one of these catastrophes is kind of a harbinger of our changing climate. But it's very important to recognize that behind each one of these extreme events, there's typically a combination of an influence from our human activities, as well as influence from just the natural variations within the climate system. And I like to use this balance as a kind of just an iconic way to just remember that it's always neither, it's not either or, it's both. And I think this is the theme of a lot of the research that I've been part of in the last decade or so. So, sources of climate change, I should really say climate changes. So on the one hand, we have our human influence on climate. On the other hand, we have natural variations. And these human activities, here are a few examples of how we are changing our climate system. The burning of fossil fuels and the release of carbon dioxide and other greenhouse gases is a primary contributor to our influence on the climate system. But in addition, we are changing the land surface through deforestation, changing our crop types, and other ways of changing the land surface that also has an impact on our climate system. Back in the 1960s and 70s, there were spray cans with these chlorofluorocarbons that were shown to deplete ozone in the stratosphere in the high latitudes of the southern hemisphere. And this is another way in which humans have affected our climate system and the atmosphere. So amongst all of these, and of course there are other examples of human influence on climate, but I would say broadly speaking, it's the burning of fossil fuels that is really the dominant contributor to our influence on the climate system. So on the natural side, we have many ways in which climate is caused to vary. And I'm going to speak a lot about what we call internal variability. And that just means that within the atmosphere and between the atmosphere and the ocean, the atmosphere and the land, the atmosphere and snow and sea ice cover, these can exchange energy and momentum and moisture and create variability on a range of time scales and a range of spatial scales. And this is a primary contributor to our natural variability. But also, of course, we have a sunspot cycle, roughly 11 years. We have the cycles of the Earth's orbit around the sun, and this, of course, can also contribute to climate variations. And when volcanoes erupt and spew sulfur dioxide up into the stratosphere, that can cool the planet and obviously have an impact on the climate system. But I'm going to emphasize this combination of factors, the burning of fossil fuels on the human side of the scale, and then the contribution from this internally generated variability in the climate system. And finally, in addition to this balance, which is important at whatever scale you look at, one has to be very cognizant of the spatial scale. that one is interested in. So on the one hand, the global view, the planetary scale view, that's maybe more simple because it's an exchange of energy in the system. And on the other hand, Dane County, that's going to be much more influenced by natural variability because it's such a small part of the globe. So whenever we talk about the relative balance of human and natural influences on climate, it's very much dependent on that spatial scale, global versus local. Okay, so for the outline of the talk, first I want to spend a fair amount of time just going through the basic science of human-induced climate change. And then I'll speak a little bit about the sources of internal climate variability, the primary ways in which climate just has natural fluctuations. And then I will come to climate modeling, and that's where we will unveil what those maps are and understand what they tell us. And we'll also look at climate projections from our Earth system models, and that's where this notion of a range of outcomes is very important. And I'll end with a brief summary and outlook. So as I mentioned, we will get to this set of maps maybe in the middle part of the talk. Okay, so first I'll begin with the core concepts of human-induced climate change. Probably this is a review for many people, but I think it's good to ground us in the core concepts. And just to really emphasize that this is based on direct measurements and the laws of physics. This is irrefutable. And the concept here of global warming is really at the heart of it is the increase in atmospheric carbon dioxide concentrations that we have been able to measure since the late 1950s. And this very important record of CO2 was really pioneered by Charles David Keeling. He was a geochemist at the Scripps Institute of Oceanography. I had wonderful fortune to speak with him on several occasions. He was very humble and just very interested in the science that we were doing. So his measurements come from this pristine environment of the Mauna Loa Observatory in Hawaii. And here is the latest graph of the atmospheric CO2 that I pulled from the Scripps website just a few days ago. So this goes from the beginning of the record in January 1958, and the last data point that you see is February, so just a few weeks ago. And very clear, inexorable rise in the CO2 concentrations measured at Mauna Loa. And fossil fuel burning is behind this trend. I'll speak about that a little bit more as we go along. So I was born in 1961, so this graph covers my lifetime, and wherever all of you sit, you can see how much things have changed over your lifetimes. But over my lifetime, CO2 has increased by 1/3. That's incredible. And in fact, there's maybe a little bit of evidence for an acceleration in the CO2. So that is primarily, or that is fully due to human activity, burning of fossil fuels. You can also see the ups and downs in that black curve. That's the seasonal variation due to plants, due to their respiration and taking in CO2 and exhaling, if you will, oxygen. And that seasonal variation is superimposed onto this upward trend. So this is one site for the CO2 measurements. The Scripps website also has a beautiful a transect of stations that goes from the Alaska all the way to the South Pole, coming through the Pacific. And here, this is only updated through 2015. I couldn't find a more recent update on the website when I looked. But here I've labeled each one of these curves and where they come from. And the important thing here is you can see that that upward trend is, it does not depend on the location. So this is, an indication that our CO2 is very well mixed in the atmosphere, and it doesn't matter where you are taking your measurements, you can find that same rate of change over time. Of course, what is different in each one of these locations is the amplitude of the seasonal cycle. And you can see there's very little seasonal variation at the South Pole, and as you go farther north, and especially Alaska, that has a very big seasonal cycle to the CO2. And this makes sense because if it's driven by plants, vegetation, obviously areas that have more active vegetation, that is going to drive a larger seasonal cycle. So I just think this is a really impactful way of seeing that this upward trend in the CO2 is, without a doubt, it is occurring worldwide, and we have measurements to show this. So that's the view from 1958, my lifetime, roughly. The view from the last 2,000 years. So this comes from a set of Antarctic ice core records, and the ice has bubbles of air trapped in it, and that those bubbles of air can be measured for their constituent molecules, and the amount of CO2 can then be backed out from those measurements. So 2,000 years, you can see very steady amounts, around 280 parts per million. And then starting around 1900, Industrial Revolution, there's a slight increase. And then finally, the Mauna Loa record that starts in 1958, you can see that extends, or this accelerated rate of increase. So if we go back 2,000 years, we've had a 54% increase in CO2 over this last 2,000 years. And if the rates of change that we are witnessing in the last few decades continue, we're on track for a doubling of CO2 in about 30 years. So I would say probably most of you in the room will witness this milestone, and I think we shouldn't be proud of that. So that's 2,000 years. I'm going to take you back even farther, and this is the last 800,000 years. So here, this is based on, again, ice core records. And here you see a somewhat different picture, and you can see these fluctuations roughly every 100,000 years, and these are the glacial, interglacial cycles. And there's sort of a feedback between the CO2 and the glacial, interglacial cycles. Anyway, there's variability, but when you look at this, our lifetimes, we're off the charts in terms of how much CO2 now is in the atmosphere. It is unprecedented over the last, when looking over the last 800,000 years. Okay, so then number two in the just the core concepts of human-induced climate change, we know that the increase in CO2 is due to human activity. And one way that this is known is that plants, when they photosynthesize, take sunlight and take up or use sunlight to photosynthesize CO2, they preferentially take up the lighter isotope of carbon, carbon-12, as opposed to carbon-13. And this leaves a fingerprint, if you will, in the wood of a lighter, more light isotope, carbon-12, relative to carbon-13. So when this tree falls and is buried and becomes a fossil fuel, it retains that signature of enhanced amounts of the light carbon-12 isotope. And then when we burn that, when it turns into coal, and when we burn that, we can actually measure, here's an example, measuring with these spectrography measurements, we can actually see this fingerprint of an increase in the lighter isotope relative to carbon-13. So that's one way that we know that this CO2 increase is due to human activity. Okay, so the third core concept is that CO2 is an efficient greenhouse gas. It's not the only greenhouse gas, but it is one of the most efficient ones. And so very briefly, as I'm sure we're all familiar, the greenhouse effect, so we have sunlight heating our planet, and some of that is reflected, especially from snow and ice-covered surfaces, and then a lot of the radiation that's emitted by the sun is absorbed by the Earth's surface. And then, of course, to come into some kind of balance, heat balance, the planet emits radiation in the form of infrared, and CO2 will absorb this infrared radiation and re-emit it in all directions, but including downward. And that is what causes this additional warming, so-called greenhouse effect. And then there's a strong feedback as the planet warms. The air can hold more moisture, and water vapor is another potent greenhouse gas. So you're kind of leveraging the CO2 with the water vapor to actually double, roughly, the greenhouse gas effect. So that's the basic physics, and this has been known for a very long time. There was a chemist, Eunice Newton-Foote, who wrote a very influential paper back in 1856 on this effect. And then John Tyndall, a physicist around the same time, did laboratory measurements to really demonstrate the greenhouse gas effect. So I just digress here. I was at the, I think it's called the Indie coffee shop, and I walked into the coffee shop. I was pretty tired yesterday morning, and I got my coffee and I sat down, and then I looked over, and I'm pretty sure I saw Eunice Foote's photograph. So I would like anybody who goes there to tell me if I'm totally out to lunch here, but I swear she was looking at me, and I couldn't believe it. So it's if you walk into the coffee shop, it's just leaning against the wall on the left, and it really looked like her, but maybe I was hallucinating. Anyway, kind of a coincidence, I would say. Okay, so then the fourth core concept is that if you increase atmospheric CO2, you will enhance the greenhouse gas effect. You will trap more energy in the climate system, and that energy will be used to heat and warm the Earth. And Svante Arrhenius, a chemist in this late 1800s, early 1900s, he was maybe one of the pioneers to do calculations to show that if CO2 doubles, one might roughly expect a warming of the Earth as a whole by about 4 degrees Celsius. I also have found out that I'm actually related to Arrhenius, which is amazing. It's through my mother's sister's husband's father, something like that. It's not an academic lineage, but it's kind of, feel like I should honor that and say that out loud. Okay, so what is the evidence for that we are witnessing this enhanced greenhouse gas effect from increasing CO2? Well, probably the most important measurement is just to measure how much energy the ocean is now storing, how much heat is in the ocean. And we have measurements, enough measurements that go back, again, maybe coincidentally, I don't know, back to 1958 here, to make this really unprecedented record of the global heat that is stored now in the upper ocean, the upper 2 kilometers, which stores most of the heat in the ocean. And again, you know, there's no doubt that this is a very monotonic, very clear rise in the amount of heat that is being added to the upper ocean. So this is, we don't live in the upper 2 kilometers of the ocean, so here is the global air temperature. This is, again, direct measurements, a mix of station data over land and also measurements from ships and collections over both land and ocean. And this record goes way back to January 1850. And again, I show you the most updated version. These are monthly values, and a baseline climatology has been subtracted out, and that's over the 20th century, from 1900 to 1999. So you're looking at departures from that time period. And I just thought I would point out our so-called Paris Agreement, which is, you know, the point at which we think, you know, dire consequences are happening if with global warming. That's 1.5 degrees Celsius. We are pretty much there. So on the right-hand axis is degrees Fahrenheit, so 2.7 degrees Fahrenheit. So you can see a real acceleration in the rate of air temperature warming over the globe, and we are now pretty much at the Paris Agreement if you look back relative to the late 1800s. So this is land plus ocean, and you can see it's a little bit, you know, a little bit spiky, a little bit noisy. Here is the record for just the land stations. And here there's, again, much more, a little bit more, you know, ups and downs from month to month and year to year over the land. But now the scale is pretty different. So over land, we are now, relative to the late 1800s, the global land surface has warmed about 2.5 degrees Celsius or 5.5 degrees Fahrenheit. It's really, yeah, it's enormous. Okay, so I'll show you one more set of time series and then we'll move on. But I just thought this was a nice, interesting way to look at things. So this is a set of time series. There's a nice web tool called the Climate Reanalyzer that people can play with, and you can make time series for pretty much any region that you are interested in. So this is for the global average air temperature, so similar to what I showed you before, but now I'm showing you the average for each year. So the previous curves were month by month. These are annual averages, and a baseline from 1951 to 2000 has been removed just to show the departures relative to the baseline. So the scale on this curve is about, from top to bottom, is about 2 degrees Celsius, so consistent with that 1.5 degree warming for the globe as a whole. So how does that look for the US? So here's the United States average annual air temperature. And again, very clear rise in temperatures, but a little bit more ups and downs than you see for the globe as a whole. And that's beginning to show us the influence of natural variability as the spatial scale that you're looking at becomes smaller. So even for the continent or the US as a whole, we have this mixture of year to year ups and downs superimposed upon this long-term trend. So in terms of magnitude, the scale for the US curve is 2.75 degrees C. So a little bit more than the, little bit higher rate of warming than the globe as a whole, but not too different. So here is Dane County. You can actually drill down into counties. And so here's Dane County. And now the range, the vertical range is 6 degrees Celsius. You can almost roughly double that to get the degrees Fahrenheit. So again, very clear, steady warming, but ups and downs from year to year. And it's kind of interesting to now start to look at individual years in the records. So I just picked 2014. That seems to be the last year when, relative to this baseline, that Dane County was actually below normal or below the average for 1951 to 2000. So the world as a whole was, you know, probably 1 degree or even more warm. And the US, not so much. And then Dane County, you guys, here you had a very, or pronounced anomalously cold year. So what does that look like? What does the map look like for that year when we're expecting, you know, global warming is going to be the primary thing that we see? Well, here is, I just show you the winter season here when the temperatures are most pronounced. So these are the wintertime temperature anomalies for that winter, 2014-2015. Tried to put the star there roughly on Dane County, and the other star is roughly where I live in Boulder. And it's amazing, you know, this very simple east-west pattern of relative cold, below normal temperatures all throughout the upper northeast and eastern or Midwest parts of the US, and then anomalous warmth in the western part of the state. So the US as a whole was kind of a wash, but each location is obviously going to show a very different temperature anomaly because of this large-scale pattern. So why was there this large-scale pattern? I'm just showing you a depiction of what the jet stream, how the jet stream behaved during this winter. And there was a pronounced ridge over the western US and a trough over the eastern US that brought that cold, you know, sustained cold, cold temperatures to the eastern part of the country. And we're going to see that this kind of jet stream variability is very important imprint of the natural variability. So that was the winter of 2014-2015, the last time that Dane County was below normal in its temperatures. Amazingly, this winter looks almost the same. A little bit shifted, maybe the cold, a little bit shifted eastward. You haven't had, you know, below normal temperatures. It was more focused in the northeastern part of the state. And now the anomalous warmth in the western part has kind of impinged into parts of the Midwest. And again, for this winter, there was again this anomalous ridge and trough of the jet stream that really was producing this pattern that was superimposed upon global warming. So lest you think that, this is always what we see, I can go back to the winter of 22-23. Things are completely reversed. And this was very warm in the entire eastern U.S. and cold in the entire western U.S. So this is really a preferred pattern of natural variability over the U.S., this east-west kind of dipole pattern. And if you take an average for the U.S. as a whole, you don't really appreciate that, individual locations can be very different from the average as a whole. But this is not the only pattern of natural variability. I can go to the winter of 23-24, and probably many of you who lived here really remember that winter as being maybe a winter without a winter, I think. And extreme warmth, temperature anomalies, those pinker colors in excess of 10 degrees Fahrenheit compared to the normal. And the entire country was anomalously warm, but really focused in the upper Midwest. So these are large-scale patterns that occur because of the natural fluctuations in the climate system. And if you want to tease out how much is due to global or human influence and how much is natural, it's kind of tricky because these natural patterns have such large spatial scales. Okay, so that now brings us to just speaking a little bit about the sources of internal or natural variability that exists simply because within the climate system. There's no external influence, but there's variations within the atmosphere. There's variability that arises because the ocean and the atmosphere are in contact with one another. And then there's variations on much longer time scales that occur within the ocean. So first I'll talk about the atmosphere a little bit, and again, bringing us to the jet stream, call this atmospheric dynamics. And this is, of course, what is behind all the day-to-day, week-to-week weather events that we are all familiar with. And as we all know, the predictability of this kind of jet stream behavior, it is fundamentally limited. And it's limited to something like less than a few weeks. And the reason for this is that the atmosphere is a very chaotic, nonlinear system, and any small perturbations will grow rapidly, and you won't be able to predict the future of the jet stream as a result of this sensitivity to the initial state. And what's important here is that just because weather varies on rapid time scales, there's actually a lot of residual variability on longer time scales, even out to multi-decadal. So the jet stream can fluctuate from year to year, but we can also see residual variability over much longer time scales. And this is a very important driver of our internal natural climate variability. So we often think about, the ocean's influence on climate, and that's going to be the main one that will influence our climate system on longer time scales, year to year, decade to decade, and also may carry some more predictability with it because of the thermal inertia of the ocean. And these are some of the names given to the leading phenomena that is due to coupling between the ocean and the atmosphere. The Madden-Julian oscillation, that is sort of a seasonal phenomenon. Then I'm sure we all know about the El Nino Southern Oscillation, and we're poised to have a strong El Nino event this coming year. Then there are two modes of variability that are operating on longer time scales, the Pacific decadal structure of variability and this Atlantic decadal variability. So these have longer time scales, and there are the mechanisms underlying these phenomena are quite well understood. But what's important for this talk is how long in advance can you predict the state of these modes of variability? And you know, it's impressive. There have been a lot of advances in the prediction skill and extending that prediction skill as models improve. And at this point, I would say there is skillful prediction of the El Nino Southern Oscillation up to 2 years, generously speaking, and then maybe up to 5 years or so for the specific decadal variability, and maybe up to 10 years for Atlantic multidecadal variability. But beyond those time horizons, we cannot tell you what state ENSO will be in, or what state this specific decadal mode of variability will be in. And then we have phenomena within the ocean caused by slow fluctuations in the Atlantic thermohaline circulation, deep convection in the Southern Ocean. These are important on longer time scales. They don't exert too much of an influence on the atmosphere, so I'm not going to belabor these phenomena. So here comes you had my balanced scale of human and natural. Here's my next icon that I like to use, which is the roll of the dice. And this is to convey that the predictability time horizon for these ways in which the natural variability within the climate system is predictable, that the time horizon is weeks to a decade at most. And beyond that time horizon, it's a roll of the dice. So, 50 years from now, we cannot say what phase or amplitude these modes of variability will be in. So this has a lot of consequences. If you want to look at climate projections out to the next 50 years for planning and management of resources, et cetera, you have to account for that you're going to have a range of outcomes, because this roll of the dice, natural variability, you can't say in advance what phase they will be in out 50 years from now. So you have to, just that's the way it is, and any planning has to account for that there could be this range of outcomes. So we have human-induced climate change, and then we have this natural variation that can be in a positive, negative phase. It can cause warming in the East Coast or cooling in the West Coast, and we can't say in advance what that will look like. So this actually complicates quite a bit how we evaluate our climate models, and it also complicates how we attribute changes that we have seen in the real world. Makes it more complicated to say what part is due to human influence and what part is due to natural variability. Okay, so now I'm going to move to, we'll get to that eye candy that you have on your brochure there. And I will just give you a brief conceptual introduction to how we run our climate models, our Earth system models, and how we make projections, and how we understand what has happened in the recent past. So as Dan said, I will talk about what is called in the field now, we call this initial condition large ensembles from climate models, and I will tell you why we use this terminology. But I would say that this really has become the way to look at climate variability and change in a kind of holistic fashion, and climate modeling centers around the world now adopt this framework of running initial condition large ensembles. So I'm going to walk you through an example that is generic, but I'll use as the example the model that I have used in a lot of the work I've been part of, and that's the NCAR Community Earth System model. This is one of the most credible Earth system models that exists in the world. We're now building version 3, and advances have been made over the years, and each version becomes a little bit better. So what do these Earth system models look like? This is the case of the Community Earth System model, but it's generic across most of this class of models. So these are global models. Typically, right now, they are run at what you would consider a coarse resolution, which is about each grid cell encompasses 4 Dane counties. So we cannot tell you what's going to happen in Madison. That's the scale at which computing resources allow. We're now at the frontier of running these models at just a fraction of this resolution, so more like 3 to 10 kilometers. So we're becoming, these global models are becoming much more high resolution just now as we speak. And these are coupled models. They have representations based on laws of physics for the atmosphere, the ocean, the cryosphere, land, some biology, both marine and terrestrial representations are also embedded in these models. So I'm not going to go into any detail, but they are models that represent the different components of the climate system. So here is how these experiments are run, and these are experiments that are then reported in the Intergovernmental Panel for Climate Change reports, the IPCC, that really helps to guide policy worldwide. So here's our crystal ball, and this one is CESM, the Community Earth System Model, and this is our way in which we make projections. So this is our global coupled climate model, and then we add to it, or we specify a particular, what we call radiative forcing pathway, so a certain prescription of CO2 concentrations, or now CO2 emissions, and other gases, other aerosols, other ways in which humans are altering the atmosphere. And so we typically, in the case of the CSM version 2, we start each of our projections or simulations back in the pre-industrial world, 1850, and then we run it forward typically to the end of this century, 2100, and all the time the CO2 and other gases are human-induced effects are ramping up during this time. So the new thing here for initial condition large ensembles is instead of just running your model one time, running your experiment one time, we run it lots of times. And in the case of the CSM version 2, we ran it 100 times. And that seems a little crazy, but I'll show you why. And of course, if the experiments were identical, then they should all give the same results, but they're not quite identical. And the only difference between each of the experiments, it's the same model, the same amount of CO2 increase, and all we have done is slightly perturbed the starting conditions of the model. And it's a tiny perturbation. It's the butterfly effect. You couldn't measure it. It's 10 to the minus 14 degrees Kelvin. And that is all that is needed to start to set these different runs or simulations on a slightly different trajectory of internally generated variability. And that's, whoops, I have some edurome thing here. I don't know what that is. So this then leads to this range of outcomes that was in the title of the lecture, and that's that roll of the dice of the internal climate variability once you are beyond the skillful prediction time horizon. So then this range of outcomes is just because you have this superposition of the human and the internally generated natural variability. So finally, we come to the eye candy, and here it's an expanded version. On the brochure, we just showed you 9 of those panels, I think. So here is what came from the paper. So there are 28 different experiments shown here, all with the same model, all with the same amount of CO2 increase, and only slight changes in the initial conditions. So these are maps of the temperature change. When I wrote this paper, we had wanted to use temperature change over the last 50 years. And so kind of arbitrary, but chose this period 1963 to 2012. The maps look very much the same if I update it to present day. So the exact time period doesn't matter, but the point is that these are changes over 50 years. So it's a very long time horizon. And you might expect that over a 50-year time horizon, these would look alike because each one of them is subject to global warming. And they look very different. And when we got these results, I think everybody in the community, myself included, was really surprised that you could even have in those blue colors, despite global warming, despite the Keeling curve going up, you could actually have cooling in large portions of North America. And that's because the naturally induced internal climate variability was so large that it overwhelmed the warming due to greenhouse gases. So can we believe this model? How do we even validate the model given all these different outcomes? There's a whole range of questions that one could start to ask. But let me show you what the real world looked like in its temperature change. We have measurements over this time period. So here's the real data. And the real data, there was a lot of warming, and it was maybe a little bit less in the far western US, a lot of warming in Canada, the Great Lakes region, and a little bit in the Northeast. So you would say, wow, that's got to be human-induced. It's warming everywhere. That would be kind of the first thought about the attribution. But here I'm pointing you to one of these, random rolls of the dice of this experiment, and you can see that actually the model is fully capable of reproducing how the real world behaved. So the model seems like it can do a good job. So we have credibility in our model, but that's not the only possible outcome. According to this model, we could have seen, cooling. It just happens that this model run actually does match the observed warming rate. So this is actually a really important point. And in the days before large initial condition ensembles, when you only ran one experiment for each model, you don't know which one of these you would get, and you might misattribute the impact of global warming if you only, say, simulated, if you only had one of these experiments. So this really, I think, is eye-opening for the community. So I want to now take this apart and show you, I'm going to show you in parallel the model world and the observations. So again, going back, it happened that the roll of the dice number 7 was the one that looks most like the observations. So that's what I've picked out here in the upper left box, and then you can see the observed temperature change over this 50-year period in the lower left. So in the model world, we can very accurately dissect what is behind this trend in this particular experiment, number 7. And the way that we can do that is that when we average all 100 experiments, the phasing of the natural variability, which is random, can be averaged out. And then it will reveal what is common to all of the experiments, and that is the human-induced component. That's the greenhouse gas-induced component. So so that's what I call the ensemble mean. So the average across all the experiments that reveals the impact of the buildup of CO2. And you can see it warms the entire continent and warms more near ice-covered regions and a little bit less as you go farther south. Then we can subtract that from what actually occurred in this run number 7, and then you get that middle map. And that, we know, in the model world is due to the natural variability. And you can see warming to the north and cooling to the south, these large-scale patterns, and they are on a par, the amplitude is on a par with the amplitude of the human-induced warming. So you can't ignore them. It's that balance, that scale, and both are very impactful for this particular run number 7. So in the observations, we don't have the luxury of, replaying the tape of history. So I don't have other realizations of our real world to show you, but we do have some techniques to try to decompose the observations. I can't go into any detail in this lecture. I'd be happy to talk one-on-one after, but we do have some techniques where we can assess in the real world what is due to the variability of the jet stream, which is primarily this internal natural variability, and that circulation-induced component is what we call natural, and that's what I'm showing you in the middle there. And then I can subtract that from the actual observed trend, and that's how I deduce as a residual the human-induced component. And it's quite remarkable. So these lower maps have no information of the model. It's a whole different technique of analyzing the observations. And I find it quite remarkable that we can actually uncover a human fingerprint that looks a lot like what we expect from first principles, from the laws of physics that is encoded in the model. So here's a fun thing, which, I wouldn't even have thought of this question had it not been for the model initial condition large ensembles. So the model tells us, there could have been many different outcomes. So could another reality have been possible? Could we have had a different outcome in the real world for the observed temperature changes? So again, I'm not going to go into detail on our techniques here, but we can take all of the natural variability that we observe in the observational record, and we can be clever about how we shuffle it in time. And so we're kind of creating surrogate sequences of natural variability that we can then add back on to the forced response. So here is one example from, we have several papers. This was a former postdoc, Karen McKinnon, that she worked on during her postdoc. And this is, again, an empirical observational way of getting at an alternate reality. And I obviously picked this particular alternate reality because it has some resemblance or showing these large-scale patterns. So the real world, according to this technique, it didn't have to be warming everywhere. And I just think, it's important to think about that, we live in one one history, and we're going to live in one future, but there are other possibilities that could have occurred. Okay, so now I'm going to move on to climate projections, and then we'll wrap up. Okay, so again, our model crystal ball for climate projections. And, oops, oh, doesn't want to advance. Okay, here we go. So for this example, I'm going to pick the same large ensemble project with the community Earth system model that I showed you before. And I've picked out this example instead of showing temperature, which we have in other papers. It's interesting to look at precipitation, and in particular, picking out the winter precipitation, which is very important, at least where I live, in terms of snowpack and all the hydrology that goes on. So hopefully this works. Okay. So I'm going to show this to you in a little bit different way. I'm not going to show you each of those individual experiments. I'm just going to cut to the chase and show you how this model responds to the imposed buildup of greenhouse gases that we have prescribed to each one of these experiments. And when we average them all together, we know that we are able to isolate the human influence because the natural variability just has random phase amongst the different members, so it averages out. So I like to say this is what we expect from human-caused climate change. This is, in this model, the change over the next 50 years, roughly, of wintertime precipitation that is due to the buildup of greenhouse gases. And I'm just showing you, obviously, North America. So North America as a whole in winter is expected to get wetter. You can begin to see some drying over Mexico. This is a very well-known pattern and quite well understood pattern that is also seen in other climate models. So that's what is going to be underlying each of the experiments, this human-induced increase in precipitation. So that's what we would expect, but that's not necessarily what we might get. So we're only going to get one rendition of this roll of the dice of the natural variability. So I'm not going to show you all 100 experiments. I'm just going to show you kind of the bookend experiments. But they're equally plausible. That's the whole point. So here is one of the 100 members, and I picked it because it's it lies at the 95th percentile of the wettest outcomes. So it kind of, it's still a very plausible outcome, and it's at the 95th percentile. So it's an extreme, but it's not implausible. And this one looks quite a bit like what is caused by human climate change, human-induced climate change, but the amplitudes are much stronger. I mean, this is big news for California and the whole East Coast. They would get much wetter than anticipated just from human-induced climate change alone. So that's on the wet side of things. We can look then at the other side of the distribution, the 5th percentile of the driest members. And you can see now the whole southwestern US and southern US is now projected to become very dry. And this is with the same amount of greenhouse gases 50 years into the future. It's kind of amazing that it can be so different between from one experiment to another. But these are both within they span what I call the plausible range of outcomes according to this model, just simply due to the superposition of this internal variability, the roll of the dice, and the human-induced climate change component, which I show as a hammer. So those are my examples, and I just wanted to keep it short and sweet, and I'm now going to wrap up with just some brief, broad brush summary and outlook, and then I'd love to open it up for questions from the audience. Okay, so just things that I hope you will take away from this lecture, that it's not either or. Natural variability is superimposed upon human-induced climate change, and this is not just for individual weather events or individual years, but even for changes over 50-year time horizon, that we always have to be very aware of both the human influence and the natural influence, and especially on regional and local scales. The planet as a whole is going to warm, and we know that is just dictated by fundamental energy constraints. But what happens where we live is much more nuanced, and it's going to be very much impacted by the phasing of these patterns of natural variability. So, and then, so that's one thing I'd like you to take home. Then this natural variability is largely due to this chaotic nature of the jet stream, of atmospheric dynamics that causes our day-to-day weather, and then also, of course, this coupling between the ocean and the atmosphere that gives rise to El Nino events, La Nina events, etc. And that's the origins of this very impactful natural variability. So maybe I'm repeating myself, but then a consequence is that this natural variability creates this range of outcomes, not only for future projections, but also for historical trends, and especially at these regional scales. So again, it makes it more interesting, in my view, to try to interpret past trends, because you now do have to think about what is the role of the natural variability versus the human-induced climate change. And then when we look at these very long time horizons that are beyond our ability to predict them skillfully, then we know that this range of outcomes is irreducible, and due to this limited predictability. So when, I used to use the word uncertainty. So we can't tell you for sure what things will look like 50 years from now. But I don't like the word uncertainty, because we know it's not uncertain. We understand the physics that is behind this range of outcomes. So it is a certain range of outcomes, and that has to be planned for. And then finally, I haven't shown you too much of this, but there are many studies out there showing that this very impactful component of natural variability, it complicates how you evaluate your model. Because if you only had one experiment, you don't know if you've really covered all the outcomes. And maybe your model can replicate past trends in the real world, or it can't. But you might be incorrect in deducing whether the model is skillful or not, because if you only have one experiment. And of course, it complicates how you attribute human and natural influences on the observed climate record. And then just to remind us that the one realization of the tape of history is not the only one that could have occurred. I just think that's, for me, actually very interesting to think about. So as we move forward, not sure what happened. So I think as an outlook, just two aspects. Now we really have the ability to, with our computational resources and other methodologies, we are now at the cutting edge of building higher resolution global coupled Earth system models. And I would say our whole climate research community is very excited to see whether there are any quantitative and qualitative changes to the picture I've been painting for you based on our 1-degree models, whether these higher resolution models will change this view in any qualitative way. So we have to stay tuned. And then, of course, the now very urgent or use of AI methods, and whether they will can be brought to bear on decadal prediction, and whether they can extend skillful prediction beyond the timescales that we currently have. So I will leave it there, and thank you so much.
If you have questions, please come to one of the microphones on the side here, and feel free, and we'll moderate questions for Clara. I'll start. So I'll start.
Okay.
Thank you very much.
Yeah.
It's always amazing to see these large ensembles, especially coming from a history of having a single ensemble. Yeah. As you say, as you get towards more regional scales, you're not able to average over the spatial variations. In the oceans, you're averaging over the temporal variations. Do you see more of a consistent picture for predictions of things like marine heat waves and these things?
Sorry, the question is what?
The question is, do you see a more consistent picture for things like marine heat waves, or for projections of ocean conditions?
It's a good question. I have to think on my feet, which is not so easy after a talk. In general, regions over land in seasons that have a lot of variability, like our winter season, the natural component is going to be amplified relative to the global warming signal. And that will be over oceans, especially oceans that are well mixed to very deep depths. Then that will integrate the energy that is being trapped through the greenhouse gas effect. And I think one would see less of an impact of natural variability. But there are surprises. The real world always is challenging. And we've recently witnessed in the last 3 to 4 decades a cooling of the eastern tropical Pacific Ocean. And this was not anticipated. Climate models indicate that that region should warm if the only influence was CO2 increases. And it has shown us now cooling for several decades. So it's a very, very hot topic, active area of research for climate scientists, whether we are missing fundamental physics in our models, that is, why we're not seeing this cooling in our climate models, or whether this is just a very sustained phase of the specific decadal variability, mode of variability. But regardless, that is what the real world has shown us, and I think that that is indicating that this range of outcomes is also very impactful over the oceans. Yeah.
Yeah, as far as constructing models, do you think it would be advantageous to include demographic growth in human population, have different scenarios for possible trends in human population growth as a factor that might exercise influence on future climatic change? Thanks.
Yes, thank you so much for that question. Yes, and that is captured with these different, we call them radiative forcing pathways. The latest ones are dubbed or termed socioeconomic pathways. So they take into account, different scenarios for demographics. And these large ensemble types of experiments are being run with these different scenarios for demographics. I haven't shown you any of that, but again, conceptually, each one of those pathways will also, be subject to the same, balance between the human and the natural influences. But thank you for the question. Yeah.
Hi, somebody in the room will know the answer to this question.
Yeah.
You had early a nice graphic with the physical systems, the ocean, the cryosphere, biosphere, atmosphere. Another graph that talked about El Nino and other longer, regularly varying features.
Yeah.
What's the percentage of variation that the regular features account for in the variability of the atmosphere? The regular features versus the physical features of the climate system?
So do you mean distinction between the ocean atmosphere modes of variability versus just within the atmosphere?
There are regular, cycles. Again, I don't know what they are. El Nino, the decadal oscillations.
Yeah.
One could presumably predict the weather with the climate, at least general climate,
Yeah.
with only those regular cycles.
Yeah.
You'd be missing something. How much forecastability is in the regular cycles versus the physics?
Yeah. So if I understand your question right, which is a great question, again, the predictability of these regular cycles, and they're not regular, which is why we can't predict them beyond, a couple of years. If they were regular oscillations, then we know what's going to happen at each time. So they also lose predictability because of their irregularity. But over the U.S., I would, and I actually can back this up with some published work, it's actually the physics within the atmosphere, this nonlinear dynamical system, that dominates the natural variability over most of the U.S.
Again, there's some impact that the natural, semi-regular cycles have. Is that like 10% or as much as the physics?
No, it's maybe like 20%, 20 to 30% in some regions. Yep.
You used a term, residual variability.
Mm-hmm.
And in the latter part of your talk, you were looking at 50-year kind of trends.
Yeah.
If you extended that to a longer term,
Yeah.
would the plus or minus
Yeah.
the 5 and 95th percentile converge more,
Yeah,
or does that still persist?
A great question. It will converge more if CO2 continues to go up. And yes, on a 100-year trend, the amplitude of the natural variability would diminish. So it would converge more, absolutely. But again, if I look at just out to 30 years, then we would see even more variation than we see with the 50 years.
So your residual trend has a lot to do with your averaging period and whether you're capturing partial phases.
Absolutely. Yep, the time horizon and the spatial scale of interest. Yep.
And then I just wanted to make a personal comment.
Yep.
I know NCAR is going through difficult times.
Yep.
I think the work that NCAR has done in Earth system modeling and in climate modeling in particular is fundamental to science. For the planet, I know that may not be what we want to amplify right now, but it is a fact.
Sounds like you might have just answered my question, but I was wondering, basically, if you compare the magnitude of the internal versus the external forcing, seems like it's gotten to about 1 to 1. Seems like that ratio is not stable in the sense that eventually the external variability dominates. Just wondering if you had a time outlook on like, what does that ratio look like over the next 200 years of climate science?
Haven't quite done that calculation. It's a really good idea. People do something called time of emergence. So of the human-induced, when does the amplitude of the human influence exceed the sort of, one standard deviation amplitude of the natural variability? And that's the time at which, that's an important time, because then, this ratio will start to go down. So there are many publications, happy to point you to them, for this time of emergence, making maps of that for different quantities, air temperature, ocean temperature, precipitation, snowpack, sea ice loss, and they're all different, depending on the quantity that you're interested in. So it varies. One recent example, especially in my neck of the woods, is of course this so-called millennium drought. So we've been in this mega drought since about the late 90s. And it's this year is going to be one of dire low snowpack that's just going to add to this issue. So there've been estimates of time of emergence of aridification, i.e., when when you're in now sort of a prolonged drought state, and I think that for most of the western U.S., that time horizon is within 10 to 20 years, according to some publications.
Thank you very much.
Yeah.
I have a question about how you choose how you initialize or decide on the perturbations for the ensemble. How do you make the decision on the variables and the magnitude, and how sensitive do you think the results are to some of those features?
That's a great question. So I didn't choose how we did it. The people who design and run the model, this is their technique. So they take you can take a single grid box in a temperature in a certain portion of the atmosphere, and you can just make this tiny perturbation, or you can start by perturbing a grid cell in the ocean and its temperature. It really doesn't matter where you start. You can change the entire ocean condition. If you do that and you start in a different phase of some slowly varying ocean mode, like this Atlantic meridional thermohaline circulation, then you can carry some memory of that initial state forward, maybe 10 years or so. If you do this tiny perturbation of the atmospheric temperatures, then that memory is, gone within a few weeks, the predictability time scale limit for atmospheric dynamics. So it doesn't matter too much. I mean, if you're, once you get beyond the longest lived predictability time horizon, you're now in this world of random phasing of the natural variability. So there's definitely discussion in the community of doing maybe coordinated experiments and ways of initializing these large ensembles. And different modeling centers do it differently at this point. I don't think it's actually that big of a deal. As long as these initial condition large ensembles, their purpose is not prediction. Their purpose is to show us, what the human-induced climate change signal is, and what then the range of outcomes could be because of the natural variability. If you're just doing prediction, you don't have to run them 150 years. Yeah,
Thank you.
thank you.
Hello.
Hi.
I'm interested in the spatial variability of temperature and precipitation amongst ensemble members. So are there any regions that stood out to you as having more variability or less variability?
Great question. And yes, you can quantify that by taking, stacking all the ensemble members and then computing at each grid box the amplitude or the standard deviation of their trend. And then you can see there are definitely some hot spots of variability in different quantities, precipitation, temperature. And what's important is how big that range is relative to how the amplitude of the human-induced component. And that's sometimes cast as a signal-to-noise metric in our climate models. And it's a way of, it's a little bit like the time of emergence. How large is the human-induced climate change component relative to the natural variability? But when you make maps of signal to noise, you don't really appreciate that the natural variability has large spatial scales. And that's why I like to also show the actual individual ensemble members.
Thank you.
Thank you.
All right. I want to thank Clara once again for a wonderful talk. And, it occurs to me, you made a career in understanding these climate variability and understanding natural climate change. And now these new methods are being used by the community to better plan for both climate change and the variability that comes with it. So it's really impressive to see that trajectory. Thank you so much for sharing that with us.
Thank you, everybody.
Let's thank Clara once again.
Thank you.
And I invite everyone to join us for a reception afterwards where we can ask
Great.
individual questions, and feel free and come up and talk with any of us as well. Thank you all for attending,
Yeah.
and please join us at the reception.